Today, we're cracking open the secret behind the most powerful object humanity has ever built. This is the blueprint for the hydrogen bomb, a design that is, all at once, a work of absolute genius and a source of ultimate terror.
And just think about this for a second. Every single thermonuclear weapon in every nuclear arsenal on the planet today is based on this one fundamental concept. So we're not just talking about a bigger bomb here. This is the design that unlocked destructive power literally thousands of times greater than anything the world had ever seen before.
And that really is the central puzzle, isn't it? The secret here isn't just about using more explosives or brute force. The real challenge, the physics problem that seemed completely impossible, was this. How do you create, contain, and control the conditions found inside a star, and do it here on Earth, even for just a few billionths of a second?
So, to really get why the solution is so brilliant, you first have to appreciate just how massive this puzzle was. This wasn't a problem you could solve with bigger sticks of dynamite. It required a completely new way of looking at the universe.
Okay, so at the heart of all this are two totally different nuclear processes. A regular atomic bomb, the kind used in World War II, works by fission. You're splitting heavy atoms like uranium, which releases a huge amount of energy. But a hydrogen bomb, a thermonuclear weapon, gets most of its incredible power from fusion, slamming light atoms, like isotopes of hydrogen, together, and that process releases way more energy. So what does it take to get a fusion reaction going? Well, you need temperatures somewhere between 50 and 100 million Kelvin. To put that in perspective, that is hotter than the core of our own sun. The only thing on Earth that can generate that kind of heat is a fission bomb. And that, right there, creates a huge paradox. And here it is, the big dilemma. A fission bomb explodes outward with unbelievable violence. So how could you possibly use that outward rushing explosion to crush a separate bucket of fusion fuel? Logically, the blast would just tear the whole thing to pieces long before it ever got hot enough or dense enough to ignite. For years, this just seemed like a complete dead end. The breakthrough, when it finally came, was totally counterintuitive. And honestly, it's just brilliant. The key wasn't to use the physical blast wave from the trigger at all. No, it was to use something else it produced, something much faster. This is it, the big idea, cooked up by Teller-Ulam and Edward Teller. A two-stage weapon. The first stage, what they call the primary, is basically a small fission bomb, but its main job isn't the blast. It's to act like a giant, super intense flashbulb for the second stage, the secondary, which holds all the fusion fuel. And here's the absolute genius of it. When a fission bomb detonates, up to 80% of the energy it releases in the first few moments isn't the physical shockwave. It's an unimaginable flood of soft X-rays, a massive, instantaneous pulse of pure radiation. And this is how they beat the clock. The X-rays, moving at the speed of light, instantly fill the inside of the bomb's casing, an area called the radiation channel. They get to the secondary and start doing their work long before the much slower physical blast wave from the primary even gets close. In a race between a physical explosion and light itself, well, light wins, every single time.
Okay, so that's the theory. But what does this thing actually look like on the inside? Let's, pop the hood and take a look at the anatomy of this two-stage weapon. The whole design is just a masterclass in physics. You've got the fission primary at one end. Then, at the other, you have this separate capsule, the secondary, which is packed with the fusion fuel, usually a solid material called lithium deuteride. And running down the middle of that is a rod of plutonium or uranium, which they call the spark plug. And the space in between them, that radiation channel, it's filled with a special plastic foam that basically turns into a transparent plasma so the X-rays can pass right through it.
So how in the world can X-rays crush something? Well, that flood of radiation hits the outer shell of the secondary, the tamper, and heats it up so violently that the surface material instantly vaporizes and explodes outward. This process is called ablation. And just like a rocket engine pushing a spaceship, that powerful outward blast creates an equal and opposite inward push, an absolutely unimaginable force that crushes the fusion fuel capsule from all sides at once. It's like a rocket turned inside.
The entire thing is this perfectly choreographed dance of physics that happens faster than we can really wrap our heads around. So let's slow it down, way down, and walk through the detonation nanosecond by nanosecond.
Okay, here we go. First, the primary fission bomb explodes. In just nanoseconds, X-rays flood the channel. The surface of the secondary's tamper ablates, which drives this massive, perfectly symmetrical implosion.
This crushing force squeezes the fusion fuel and, at the same time, compresses that plutonium spark plug in the middle so hard that it goes supercritical and starts its own fission reaction. And that acts as the final match, heating the now superdense fusion fuel to millions of degrees and ignition.
The result of this perfectly orchestrated radiation implosion is just staggering. The fusion fuel gets compressed to over 1,000 times its original density. At that kind of density, the rate of fusion reactions goes up by a factor of 1,000,000, which allows a self-sustaining thermonuclear fire to finally take hold.
And once that fire is lit, the reaction is almost instantaneous. The entire fusion burn, the part that releases the vast majority of the weapon's energy, is over and done in just a few dozen billionths of a second, just before the weapon completely vaporizes itself.
But wait, the design has one final, very clever trick up its sleeve. A third step that doesn't just multiply the weapon's power, but also makes it a whole lot cheaper to build.
This is what they call the fission-fusion-fission process. You see, that fusion reaction releases this massive wave of high-energy neutrons. Remember that uranium tamper wrapped around the secondary? It's typically made of cheap, non-weapons-grade uranium-238. Well, these super-energetic fusion neutrons are powerful enough to force that U-238 to undergo fission, releasing even more energy. And get this, in many H-bomb designs, this final fission stage actually accounts for half or even more of the bomb's total destructive power.
And as you can see, the design is just terrifyingly scalable. The energy from that second fusion stage can be used to ignite an even bigger third stage, and so on. The largest bomb ever tested, the 50-megaton Tsar Bomba, was a 3-stage weapon, where each stage was something like 10 to 100 times more powerful than the last. So, we've been deep in the physics, but let's pull back and look at the real-world impact of all this. This wasn't just some theory on a chalkboard. It completely defined the reality of the Cold War, and honestly, it continues to shape our worlds right now. The very first test, Ivy Mike, in 1952, proved the principle worked. But it was the Castle Bravo test in 1954 that really showed everyone what a monster they had created. A simple miscalculation led to an explosion 2.5 times bigger than anyone expected. It created the worst radiological disaster in U.S. history and showed the world the truly catastrophic power that can now be held in a single device.
And that brings us right up to the present. You know, after 70 years of incredible technological advancement, this fundamental principle of staged radiation implosion is still the blueprint for every single hydrogen bomb on Earth. It is the secret that every nuclear state has tried to master, the key to ultimate destructive power.
In the end, the Teller-Ulam design is just this profound paradox. On one hand, it's a testament to human ingenuity, an incredibly elegant solution to a frontier physics puzzle. But on the other, it handed us the power to replicate the heart of a star right here on our own planet. I mean, the largest test released more than 1% of the sun's entire power output for just a fraction of a second. The physics is elegant, for sure, but the implications are and will forever be absolutely staggering.